The setup that we did this morning has installed the pip command in the wrong place. But if you type /user usr /local /bin/pip install line or profiler, it will work. Helpers, you may need to give some help with that, I suspect. And then, using your favourite editor, I would like you to create for the very, very small Python programs, tiny Python programs, that we're going to take a look at using the Python profiler. So there they are. There's some contents. Spaces and indentations are going to be very important here, but that's maybe some of the debugging we can do. So 4 files, call it pdb exercise 1, pdb2.py, pdb4.py, etc. So you can copy and paste that content into 4 files. So, whoops,
one question.
Go on.
I didn't run this line. The line profiler was like installed via pip install. Or does it with the kind of package that it comes?
It should be there by default. Well, it might be. So pip is the installer.
Yes.
It's the package installer. So we're using pip to install the line profile into it, if it's not already installed.
Okay.
It may be, in which case we're okay. But if not, we'll install it.
Okay, and in terms of this pip install, I have a question. So what I usually do is like, I use the packages that come with Ubuntu basically. So I use like Python, whatever, to install Python.
That's fine.
Sometimes they are out of date.
I do that as well. So you can do an update. So use apt-get, use the package.
Sometimes they're out of date.
Yeah.
It's a little insecure,
this
little sweet.
So it's a teacher by Google, and they recommend to install it by
Yes.
Then I want to extend to mess up things. If I have like a Ubuntu package that comes with this particular feature, and I install a version on top of it that might
So these are
request packages different how do you say that? Delete status of their version.
So these are also
Well, ideally they should. They
should.
Shouldn't. If they've been set up correctly, people who create repositories in each system are often the same person.
Yeah.
So the maintainers are the same people. So they shouldn't. How do I make sure it doesn't happen? I just use the one system. So I will use pip all of the time.
All the time.
Yeah. Because I know that Python, the pip being Python's package installer, rather than relying on the Ubuntu package system. So the one system you use apt-get, for example, you're relying on Ubuntu's package, whereas pip on the older two easy install.
Yeah, true, but for that, I had like I'm not sure. Sometimes I install something like pip and then other libraries kernels.
Yeah.
Like for example, something GDAL library, right? That's horrible. Doing pip.
Yeah.
Never worked.
You never got to work?
No, I never got to work with pip, but of course, it's just that I just use the Ubuntu library. So,
I don't know this information. A bit of trial and error. This is where it confuses people who've not got a lot of experience. But if you've done that, you know it doesn't work, you try and learn. You've got a set of tools you can try. That's one of the reasons why full Python packages, like Python distributions like Connet, have become so popular in these circuits. Because they shoot everything together and they've got their own package management tool that plays nicely. Hello. There isn't file 3. For exercise 3, we're going to use 2 and 4 files. There isn't a 3. Trick question from Adrian there, just to catch me out. There we go. There's a 1 and a 2, and a 4 and a 5. There isn't a 3. So whichever your favourite text editor is, whether you're a Vi or a Vim, or a Nano, or a Gedit, or an Atom. Notepad++, says Emma, and why not? Text editor. A good place to put the files would be in the directory that the git clone commands the SC leads profile. If you pop it into that direction, that's a good place to keep it. As long as they're somewhere where you can find them, that's also good.
Somebody needs it. I don't know. Whoops.
So,
Where's the first file? But there is one.
Oh, that's your editor. Yeah, sure. Yes. When you press button. Okay, so that's another text editor. So you can use Python interactively. Huh? So you just type a line and that is what you get here. But that's another text editor will create a file. Do you ever write like your code in those text editors?
Did you do the cloning step before? Okay. You should find this. Your home directory or? Your rules. Put it on the console.
So this is it. So there you go. So you can do a couple of days, or to control no to right Did I spot that somebody's managed to cut rather than copy exercise 1?
Yeah.
I think somebody's done that, haven't they?
I'm putting it back now.
Thank you very much.
It wasn't me, but I'm putting it back now.
Good man, thank you. So for those of you who just wondered what's happened to exercise 1, somebody hit the wrong button on the keyboard. Oh, there we go, it's magically back.
But did you want it to be indented or not? Because when you copy it into the new file, you have to erase the indent.
I
prefer it to be like this, where it's...
I've left it as it is, so that people have an opportunity to explore indenting when we do the debugging. So some of it might work as it is, some of it might not. But that's something for us to find out, isn't it? So I think 1 more minute, and then we'll carry on. Okay, so this afternoon we've got two 1.5-hour sessions. Myself up first, and everything's going to do an hour and a half. And this afternoon is really about 2 main things. It's how to find out where we are going, where our programs are going wrong, and how to make sure that doesn't happen in the first place. Okay, so the 3 themes as part of that are profiling, debugging, and testing, which are 3 software development practices that we should really try very hard to embed in our day-to-day practice. Edwin's going to talk an awful lot more this afternoon about testing, so I'll just say this: you should do it, or at least some form of testing. And you're not going to disagree with that, are you?
Of course I am.
Testing is a useful practice. But sometimes we need to explore in a little bit more detail how our code, how our program is behaving. So if it's exhibiting characteristics that we are uncertain of, that we do not expect, then there are a number of ways we can find out what our program's doing. And I guess we've all stuck loads of print statements in, everywhere, inside loops and inside if statements, to desperately try and find out how our program's behaving. I see you're grinning there. We do it all the time, don't we? It's a very common practice and it's a very useful tool to be able to find out exactly where our program is doing what at any one point in time. Of course, when we put those print statements in, we've got to take them all out again afterwards. It is a quick way of working out what's what, but there are better and certainly less tedious ways of looking at how our program behaves rather than using print statements. What we're going to use in the first part of this session is we're going to use one of the debugging tools, and it's the Python debugger, which is called PDB. So what I want to take a look at first of all is the very first of those little snippets of code. So let's have a look at the exercise 1. Okay, so a very trivial program, but it does something, doesn't it? So it assigns a value to a variable, it concatenates two strings together, and it prints the output. Now, I've used Python 3 syntax here for print, so if you're using Python 2 or Python 3, that should hopefully work. If you've not used Nano before, to save, it's Control and O, and to exit, it's Control and X. Okay, so let me just clear. So to invoke the Python debugger, you need to type a few things in on the command line. So first of all, it's Python -m pdb. And then the file name that we're going to debug. So it's Python, exercise. That's what that works. Just checking the right directory. PDB.
PDB again. -m PDB and then the file name.
Thank you. In my bag are my reading glasses. Sorry. I should have put those on before I started. It's absolutely shocking. I cannot see a thing. Sorry, folks. I should put my right glasses on. And then I've got an outside chance of being able to see what I'm doing. Good grief, I can see.
I was supposed to use Python 2.
But this shouldn't make any difference. I'm using Python 3. Okay. So, what we can see here is a little bit of information. So PDB is the three-letter acronym for the Python debugger. Has anybody used people used PDB before? Is this new to people? You have used PDB. You'll probably tell me there are much nicer, more user-friendly Python debuggers. Or are you happy? Does this one work
I
for you?
use this one.
Okay,
I just use that.
that's good. Okay. So we should get a prompt that looks something like that. Okay, so it's the name of the file that we're debugging and a little arrow pointing to that very first line of the program. Is that what we get? Just stick your green stickers up just to confirm that that's the case. Because if that works, I'm convinced the rest of it will as well. Excellent. Well, green stickers everywhere, green stickers everywhere. Green stickers over that side of the room. Back row, we've got green stickers. Just show me a green sticker, if that works. Good, excellent. So, what that prompt gives us is the next line that's going to be executed. It hasn't executed that line yet. It's pointing to the next line that's going to be executed. And the prompt is PDB in brackets. And that's where we can interact with the debugger. So the debugger is a program that's running our program for us. And it allows us to step through it, line at a time, inspecting how the program behaves as we do so. So if I hit N on the keyboard, and hit Enter, that will execute the line that was just displayed. So what it's done is it's executed the name equals Martin line. Yeah? And it's now pointing to the second line in the program. So what it should have done at this point is it should have assigned a value to the variable name. So the first thing that we might want to do is to see what value that variable name has got. So we can use the command P. P is for print. And we should be able to display the value of the name variable. So P name, hit Enter. So that tells me it's a string that's got the value we want. So we can step through a program line by line, and we can inspect the values of variables. Okay.
It tells you it's a string from...
Sorry, I need to put my other glasses on so I can see it. Go on.
It tells you it's a string from the quotes?
Yeah. We'll look at some numeric variables in other exercises. But that's how we know it's a string. Yeah. Thank you. I'm reading glasses back on. Oh, dear, dear, dear. So we can hit N again. N takes us to the next line. So remember, we should be executing the greeting equals hello plus name line. Okay. And that should have assigned, where are we? That should have assigned greeting, this one, a value. So inspect the value of greeting then. So what command are we going to use and see whether it has the value we think it does. So how do we do that? What command do we use? Inspect. It's P, isn't it? So we'll do a P greeting, like so, and that should have the value hello Martin, which it does, which is excellent. Does this look confusing so far with all of these brackets and modules and keys and all sorts of nonsense? And we've only got a 3-line program, haven't we? If people have used PDB before, it's really easy to get lost. You're going to say no, it's not easy to get lost. I get lost all the time with PDB. I forget where I am.
I like using it to set the breakpoint.
So you set breakpoints. Well, if there's any point we want to find out whereabouts we are, we can use the L command. Now, what the L command does is it lists the source code and puts a little bit of a pointer to tell us where we are. So if ever we lose track of where we are in the program, L to list shows us where we are in the execution. So we're almost at the end of this one now. So let's hit N to do the next line. And as you can see, it's executed the print command and it's finished. And most importantly, to get out of it, is Q to quit. And then we're back at our bash command prompt again. So, just a couple of recap pointers there. If anybody would like to pop this into the Etherpad, just so we can remember what we've done. So, remember we had a line that called Python and attached PDB to our program. Okay. So it's calling Python, it attaches PDB, the Python debugger, and tells us that's the program that we want to do, that we want to debug around. The very, very most simple commands are, what did we use to step through? What was that command? That was N line at a time. What command did we do to show us where we were, or to list the program? That was to list it was L to list. And if you want to display the value of a variable, that is P to print. Yes. So, quite straightforward. So, hopefully, you've now got a second little program. So let's just have a quick look at that. So, exercise 2. So, we've got what have we got to start? What are the first 3 lines? What programming construct is that? Just to recap, what do we call it? It's a function. And good programming practice tells us that we should try and write functions within our code, rather than just writing hundreds and hundreds of lines of nonsense. Split it up into bits that we can reuse and reproduce easily is a really good thing to do. So we've got a function, it's called greet. Ouch. And then we've got a little bit of code underneath it. For those of you new to Python, spaces, indentation is incredibly important. So you'll see under the def, we've actually got 4 spaces worth of indentation. Yeah? So if your program doesn't have that, the greeting equals hello plus name line and the return greeting line are indented by 4 spaces.
What about if you put a tab?
It all rather depends on what your editor does with tabs. We'll see. We'll see when we debug it.
What's a tab?
A tab isn't necessarily spaces. A tab might be spaces, but it might also be a tab character, which Python won't like. Okay, so let's start the debugger again. So remember, it's Python -n pdb. So that's the little incantation we use to initiate the debugger. And we're going to debug, in my case, pdb exercise 2.py this time. Okay. So we're at the start of the program. It's pointing to the first line in the function definition. So that's where we've declared the function. Well, this time, instead of going through a line at a time, we're going to execute the whole thing. And there's command C, which stands for continue execution, which will allow the program to run naturally. So this is just the same as actually typing Python pdb exercise 2.py. So let's see what happens. So basically what's happened here is the program is run from beginning to end, printed out that greeting, and then it's restarted itself. So it's put us back to the pdb prompt. So running it once allows us to see how the program behaves. It takes us back to the start, and then we can step through it a line at a time to explore behaviour. So let's use n again to walk through the script. So the first n takes us from the function declaration straight to the greeting line. It doesn't step into the greet function. We'll hit n again, that takes us to the print greeting line. And then we'll hit n again, which should execute that line, hello Martin, and that's where we're finished. So what n does is it continues execution until the next line in the current function is reached, or we return back to the main program. Okay, so let's press C again to restart. Okay. We're at the start of the function now. That's def greet name. And let's hit n. So at that point, so we're going to do a bit of visualization now. We've just executed the first line of the function, the definition line. we're about to execute the second line of the main program, which is that greeting line. What I'd like to do is not to go and carry on stepping through the main program. I want to go and have a little bit of an explore within a function. Okay, so remember what n does. N steps through, if you like, the lines of the main program. We've just started that function. So we now need to go and explore what's happening in the function instead. And instead of n, we're going to use s. So s allows us to step into a particular function. Okay? So let's see what happens now. So let's go into the function. And let's try n again. So s allows us to step into a function, and then we step through the lines of the function with n. So these two lines, where are we? Greeting equals hello plus name, and return greeting, aren't in the main program, they're actually within the function. So to get into the function, if you remember, we use the s command, that steps us into the function, and then once we're in the function, we just use n to take us in a line at a time. So what the s command has allowed us to do is allow us to go into that indentation and step through and see what the program's actually doing. So let's do n. So you notice we get a return then, and that tells us that we've left the function. And then we can just keep on hitting n until we get to the end of the program. And there it is. So that's the end of the program. And now we're back to the start. So what we've done with the s command is we've used it to step into a function and explore what the function actually does. So there's one more thing I want to do here, which is to look at a command called R. So back at the beginning. So let's hit C to restart. Okay, so we're right at the beginning now. Let's hit N. So execute that line. Let's hit S to take us into function. So at this point, let's try R. So what the R command does, instead of having to step through each individual line of the function, it takes us straight to the end of the function. It takes us straight to the very end of the function, executing all of its content, and then drops us back into the main program. And as a quick sanity check, let's do an L to list where we are. And you can see it's taken us to the point where that return is going to happen. So we didn't step through and execute the greeting line, we went straight to the return using R. So R is a really useful command to check to see whether a function is about to return the value that we intend.
Sorry, the step in 2 is working only when the function is defined. What if I want to step into the function at the definition level?
So can you give me an example of what you mean? Put my other glasses on so I can...
I mean, if I can go into the function when I execute the function.
Yes.
At the level of defining the function within the compiler, I cannot get into the actual definition of the function, the definition level. or it doesn't really need to?
No. Yeah. It's not, a PDF is not intended for that level profile. So, help's always useful. So there's actually built-in help for PDB. It's just help. Now, obviously my window is not going to display. There we go. So there's a whole load of help topics there that we can use. So we can type help on a particular command. So if we were to type help n, for example, it gives us a very brief description of what n does. It's short for next. We can do help s, etc., etc. So what we've had so far are some very trivial examples that didn't have any errors in them. But let's take a look at exercise 4. So, firstly, I would like to take a look at this program and just to try and work out what it's doing. So, just take a minute, have a chat to the person next to you, and just see if you can describe in one sentence or less what this program actually does. So, what are we trying to do here? You're stuck. You're stuck. Stuck. That's it. You'll get this pronunciation right. Do you want to quit? That's where it's just key to quit. All I don't know. So, what does it do? What does it do? Come on, expert Stefan.
Doing some magic to command line arguments that are given to this program.
So what this program hopefully is going to do, it's going to take some command line arguments, it's going to do something to them in that function def. So it does x plus y times 2. And then it prints some prettily formatted answer out. So how many command line arguments does it expect? 2. So let's just do that. Yeah, that's the whole point. The whole point is that this is not going to behave in the way we want it to do. And it's going to be your job to try and find out, firstly, what those problems are, but then how we fix them. So let's put control X again. So we run it at the command line. So Python, what is this? PDB exercise 4. py. Remember, it expects 2 command line arguments. Let's give it, I don't know, 10 and 20. The answer is 10, 10, and 10. Now, I don't know whether that's right or wrong. Let's try x plus y times 2. That's not looking right, is it? That's looking very, very bad. What on earth is going on? Now, we could stick lots of print statements in here. Who would at this point stick lots of print statements in? And put in 35 print statements in 4 lines of code in a desperate attempt to work out what is going on. And then probably there's at least 3 beers and 2 cups of coffee in there as well. And a good cry. And then finally we find out what's wrong. So, we can do better than that. Let's use PDB. Correct glasses. Let's have those. So, remember again, so we're going to call Python. We're going to attach the debugging to it, PDB. We're going to use PDB exercise 4 this time. And we're going to go into the debugging. Oh, we should give it some arguments, shouldn't we? Yeah, thank you for that. Let's give it some arguments. Let's give it 150 for the sake of arguments. Otherwise, it's not going to work out anything useful, is it? So, the first line we wanted to do, sys, is a module that we're going to need. We need those import commands out of that, so we need that. I'm happy. So let's get to the point where we've got access to those variables x and y. So where something fun happens with those variables. Let's do it again. So now we've started the function definition, def magic, x and y. Okay, I want that to happen. I want to get argument 1. So that should get me the first argument, or it should get me one of the arguments at least. So let's do n again. So that should get me x. Let's do n again. That should get me y. So at this point, x and y should have got some values. Now if I use the p command on its own, whoops. If I use the p command, with dir, so pdir gives me all of the variables that are in the current scope of the program. So built-ins file and name are Python built-ins, but magic, because magic is the name of the function, sys, which is the name of the module, x and y. Oh, so x and y have got values. So x and y exist. We at least know they exist. So all that tells me is what variables exist. So that's not really very nicely formatted. It's just a list, isn't it? Those of us a bit more familiar with Python may have come across pretty printing. Come across pretty printing? Yeah, so pretty printing allows us to have a more nicely formatted list. So let's pretty print those variables within scope. Doesn't appear to work. But x and y definitely exist. So, if x and y exist, I need to find out what value x has. How do I find out what value x has? It's px, isn't it? So px. Now, just before we hit enter, I had 2 command line arguments tonight, which were 1 and 50. So, what do we think x should be? One of those 2. Let's see. Ah, it's 1. That's good. That's what I want. Hopefully. Does anybody spot anything?
It's a string.
It looks suspiciously like a string, doesn't it? That's either good or bad. It's probably bad. Interestingly though, because the Python debugger gives us access to the Python interpreter, we can do Python within the Python debugger. So let's see what happens. Type x should return the data type of that variable. Yeah, it's a string. So that might be one of our problems. Probably is, isn't it? So y exists, doesn't it? So let's do py. Let's see what we get. Is that right? Should it be one? Remember we had two command line arguments. They were 1 and 50. So x hopefully should have been the first command line argument. Y should be the second command line argument. Is it the second command line argument? No. That's a problem. Not having much joy with this. I'm a really crap program, aren't I? And again, it looks suspiciously like a string. And it is. That's annoying. So we've already unearthed one major problem. I'm doing something wrong with grabbing my variables from the command line. So something seriously bad has gone wrong there. So that's one major error. The second major error is that they're strings. So that when I try and use the plus operator on the strings, I'm going to get some unexpected behaviour. But as a quick sort of self-check and a quick self-test, what we can do is we can convert those strings to integers, if they are integers, and let the program execute and see if we get any different behaviour. So to do that, we can say something like x equals int x, and y equals int y. So what that should have done is converted x into the integer version of itself and y into the integer version of itself. So let's see what happens now. So let's print x and y. This time we get what looks suspiciously like integers and not suspiciously like strings. How could we see whether we are correct in our belief that that is the case? What could I use to find out whether x and y are in fact some sort of numeric variable? What would it be? You can use type again, can't we? So let's try that. Let's try type x. I forgot the brackets, didn't I? Type x, and lo and behold, it looks like it's an integer. And lo and behold, it looks like y is also an integer. So this is looking quite good now.
So why isn't it space? Why doesn't it matter? I thought like this type then giving looks like a function very different versus space in between your brackets and type. This is something like e to b.
Probably because I'm using Python 3 and not Python 2.
I mean, you can do it without the space as well.
Did I do that?
Yeah.
I didn't.
So you did it before without the space.
Did I? Whereabouts did I do that? Oh, sorry. You mean up in, so I'm with you here. Third line down, is that what you're saying?
Yeah, that's how I would use it now. But now I just was wondering why the space works as well. Because
I'm assuming that this particular bit of the interpreter will strip out spaces between the end of the command and the starting set of brackets. Certainly within PDB, because PDB is an interpreter that sits on top of Python. It does work, and that's all that matters. Let's not question it too much. So we're happy now that we've got x and y. Do x and y have what we assume to be the correct values, though? No. Does x have the correct value?
Yes.
But y somehow wrong, isn't it? So it really should be 50. Yeah, we know it should be 50, so we need to keep a mental note to go back and change our code afterwards so that it gets the second command line parameter and not the first. So clearly what I did when I was creating this program, as many of us do, we copy and paste lines and we forget to change values. Does anybody do that? So, because PDB sits on top of Python, let's assign y the value 50. Okay? With or without spaces, it should still work. Okay? So, let's see where that works as we expect. So, let's just do C now to continue. X plus, what was it, y times 2? Does that look right? Does look better now, doesn't it? Yeah, so it's done the y times 2, it's 120 points. I like it. Alright, so it's a bit of a trivial example, but it has helped us to identify a number of errors in this bit of code. So, just to finish off, just give us a couple of minutes, and then I think we'll talk a bit about breakpoints. Let's bring that up. We'll mention breakpoints, I wasn't going to, but we will do. So I'm just going to give you 2 minutes to fix that program and run it. So, if you recall, so that's the one. There are some errors there. So, how do we fix them? The function itself looks fine. There's something definitely wrong here. And there's something wrong with data types. So let's give people just a couple of minutes, couple them to rest, just to have a look at that. And a quick fix, and then confirm that it actually works with 2 command line parameters. Yeah, easy stuff, isn't it? So why wasn't retrieving the correct, so wasn't retrieving the second command line parameter, was it? So what change would I make on this one in order to retrieve back the second command line parameter? What did we do there? Try it with the 2. Did the 2 work?
Yeah.
Excellent.
Yep.
Well, those strings. So, what did people do to convert those strings to integers? Did you do something really?
I wrote an int around deriving the argument from the command line.
Right, so you wrote, where did you put your ints? Around the sysrv. Yeah.
It's not a good solution, but I want that.
No, it works, doesn't it?
Only as long as I put in integers.
Okay. So, hopefully, what we've now done is we've fixed the problem we had with our program. So we've used PDB to step through the program at line at a time. We've used PDB to inspect the values of some variables, and we've used it to change the values of variables on the fly whilst we are still in the debugger. So we don't need to exit out, change the program and go back in again. We can do everything that we need to do whilst we are still in the debugging application. We do need to remember what we've done, but of course, if you're a good programmers always have a notebook and they write things down. He's a madman talking about. Paper, pens. What's the world coming to? And then finally, we'll just check it does do as we expect it to do. What did I call it? PDB exercise 4 PY. 50, 1 over. That's what we expect. I'm sure some of you have tried this with strings. So we try it with some strings, and let's see what happens. Yeah, but we'd sort of expect that. So we've only just started the debugging journey with this particular program. We've now got it to at least behave in the way that we expect. But then we need to try and make it idiot-proof. Because if there is one thing that we're almost guaranteed, that other people, your users, your collaborators, will find ways of breaking your program that you have never, ever thought of. And I'm not joking, am I? Those of you who've ever done any programming, you would be surprised. So what we've done so far is we've been stepping through the programs a line at a time, which is fine for very short and trivial programs. It's less fine for programs that are a little bit more complex. So to sort of simulate a slightly more complex program, let's have a look at exercise 5. So PDB exercise 5. So this has got hopefully something a little bit more interesting with it. It's doing a bit of timing. The timing here is quite important because I've got it to do some sort of slow subtractions. So the definition, the function definition here, of course, slow subtractor, returns a minus b, and basically it pauses before it does the calculation, hence slow subtractor. So as you can see, there's a few things down there, a few definitions, a few commands. Just have a little bit of a familiarise yourself with that. So that looks fairly straightforward. Oh, there's the line under def, where we've got the 3 double quotes at the beginning and end of the line. Have we come across that before? People come across that before? Is that a yes or a no? Is that a no, I'm assuming? It's what we call, yes, you have. Oh, see, you've not let me down. What's it called? What do we call it? It's a doc string. So basically a doc string is a string, a documentation string, that we use to describe what a function does. Okay? Think of it as a little bit of online help for our documentation. It's a command that we can use, we'll look at these tomorrow in a bit more detail, where we can tell people how our function behaves. It is good programming practice to include a doc string in every function we write. Okay? Who includes doc strings in every function they write? See, 2 of us, 4 of us. Oh, good. Most, that's good. Everybody else is bad.
Or lying.
Or
not lying.
Or not lying. Yeah, the 5 people are lying. Right. So what we're going to use, what we're going to do then is we're going to run the profiler again. Well, this time we're going to see how and why this program behaves as it does. So let's just run it to begin with, and let's just see what we get. So PDB exercise 5 this time. Maybe I shouldn't have put sleep 5 in. So it's actually called that function several times, but every time it does it, it's waited 5 seconds. Oh, there we go. Oh dear, we've got a problem, haven't we? 0 division error, division by 0. Oh, that's helpful, isn't it? So something's wrong with my experimental fraction equals experiment over total. Okay, it tells me that there's a division by 0 error. If I was trying to fix this with lots of prints, I have to run this program every time to observe the impact of the print or a slight change, and it's going to be incredibly tedious, incredibly quickly, isn't it? Having to wait 20, 25 seconds for the program to complete each time. So again, I know it's another trivial example, but it does give you an idea of how we can deal with perhaps more complex programs where we need to ignore bits of the code and concentrate on the bits that are previously problematic. So what I want to do is to insert something called a breakpoint immediately before the line that causes the error. So we can see the line that causes the error, experiment fraction equals experiment over total. So what I want to do now is go into my program again. So we're using Nano, PDB exercise 5 this time. And I'm going to scroll down a little bit. So that's the line. That's the line I need to do something with. So immediately prior to this, I want to do this. Import PDB semicolon PDB dot set trace. So what this is going to let us do is, even when we try and run the program normally, it'll execute most of the code as we expect. But when it gets to the point where we set a breakpoint, it stops executing the program, that's why we call it a breakpoint, and it drops us straight into the Python debugger, so we can take a look in a little bit more detail about what's going on. So breakpoints are exactly that. They're essentially stop lines that we insert into our program to stop normal execution and take us into a debugger session. So we'll let the bit that we know behave work as normal, but only explore in detail the bit that we want to look at. So import PDB, because PDB is the Python debugger library that we're going to use, and at this point we do a PDB dot set trace. So let's save that. And exit, like so, good. So let's try Python PDB exercise 5.py. So it's executing the program, it's doing all of those 5-second pause, 5-second pause, 5-second pause. Ah, there we go. And then it's got to the line that we set the breakpoint at. So it's dropped us, still running the program, but it's dropped us straight into a PDB debugger session. Excellent, that's exactly what we want. So we're at the line that causes the problem. Experimental fraction equals experiment over total. So we know that is the problem. What error did we get? What was the error message? Division by 0. So if it was divide by 0, I think it's a pretty good idea to take a look at what total is. Yeah, it would be, and if that's not what we think it should be, total, if you take a look back, or if you recall back, is defined in the previous line, and we'll see whether we get what we want to get. So let's try P total. Oh, well, there you go, that figures, doesn't it? So we have a problem. So total didn't get the values that we wanted. So the variables on the previous line were some crazy scientific experiments. So P, let's see what sum is. 4. P crazy.
Can you do that in a loop like the whole namespace?
We can do better. We can do P sum.
So you list the name and the values of all namespace?
Not easily. It is better to define them one at a time. So there we go. So that's listed. It looks like one of them is a little bit wrong. So the crazy variable should be the result of getting A minus B. Now, I don't know if you've got a window open with your commands, with the program rather, but I passed crazy 12 and 78. It's done A minus B, so perhaps I've got those the wrong way around. So that's probably something that I need to look up. So possibly what I've done there is I've got those the wrong way around. So let's have a look at the program itself. What is it? PDB exercise 5.2y. Yes. So AB returns A minus B. So that's going to give me 12 minus 78, which is minus 66. So let's turn that the right way around. What was it? 78. So let's run that again. So remember what it should do is drop us down into the debugger session after 20 or 25 seconds. So let's see whether that's going to happen. So for those of us that have been used to using prints to inspect the values of variables, even if all you take away from this is let's not use print, but let's do input pdb semicolon pdb.set_trace, and that's a much better way of being able to inspect the value of your variables and do something with them interactively in the PDB shell. So let's try this again. P total. Now it's got a value. Yeah, so that's what we should have expected before. So we're happy with that. So let's just do some ends. So this is where we went wrong before. And this time it hasn't failed. It went to completion. Excellent. That was good. That really is just a very simple introduction to the Python debugging. And all I've really shown you in just over an hour is how to use this instead of doing prints. But it is a far more useful tool. Yeah, far more useful tool. Is anybody tempted to give PDB a go next time they're debugging their code? Excellent. Right. So that's PDB.
And can I ask a question?
Go for it.
So one of the reasons that prints are bad is if you have loops, they might get parallelized, and if you put a print in it, it won't. So if the error you have comes from the parallelization of your loop, it will disappear when you have the print in and reappear once you put it out.
Yeah.
So how is that with breakpoints?
It all rather depends on what you're doing. It's a simple answer. Usually a lot safer.
Okay.
As we will see with the next little bit that we're going to look at, which is profiling, any time that we interfere with the execution of our program, we affect it. So debugging and profiling aren't going to affect the program. There's no escape. But usually it's a safe thing to do. PDB is pretty safe, pretty well established. So we need to just refer back to here. Look at that. People have been putting stuff out here, left, right, and centre. So let's check. Done. Right. Okay. So. So I want you to install another little bit of a Python library. So we're going to install something called line profiler. I'm just going to spend about 20 minutes there on line profile. So, to install line profile, remember we used pip install before, didn't we? So, what we should need to do is it's user, forget this right order, it's user local pip install line profile. So with line 170 is another little installation to do. So let's just have a minute to do that. Just have a bit of a pause between sessions, and then we'll crack on taking a look at what line profile is in a minute. So did pip install line profile work for people? You stick your green stickers up if that's worked, and your red stickers if not. Red sticker. That's it. Yeah. So we do pip install line profile. Yeah, you think it's worked? Good. Excellent. We'll see. So, the concept of profiling then. We've used debugging to work out where our program is going wrong. Okay. The profiling tool, or profiling, allows us to investigate in a bit more detail exactly how our code is behaving, and particularly where it's spending its time. So, often I'll write to the code, and I'll say, yeah, that's fair enough, that's good, it does the job, but then I need it to be faster, and then even faster, and then faster again. So profiling is really useful, as I said, to explore where our program spends its time. And then once we understand where it spends its time, we can investigate those bits in a bit more detail and work out how to make them faster. So, Proficient course, what I'd like you to do, just for a couple of minutes, when you look at the tables, is try and answer this question. What things, or what design principles, make code run slowly? Why does code run slowly? 2 minutes to have a think about that. Why does code run slowly? Which might give us an idea of the sorts of things we're going to look for. So 2 minutes to think about why code runs slowly. Let's have a think about that. Right, okay, any volunteers? Let's see if we can get 5 things from you. So what makes code run slowly? Why might code run slowly? Why might my code run slowly?
overhead, for example, we find which metric is for within the value, or we so a metric that grows to the really excess.
Yeah.
Instead of predefining.
So what could we call it? Inefficient memory usage? Yeah, that'll be. So you give me the example of defining a huge matrix or array to store a relative values, and assuming that's not a sparse matrix. So, okay, excellent. Yeah, so inefficient memory usage. Data structures more data than we need or something similar. Any other thoughts on what makes
Too many iteration?
Too many iterations, or doing an improper number of iterations. So it's problems with loops. Yeah, that's a good one. So something else that might cause inefficient memory usage. So we've got two issues there with inefficient memory usage. Poor use of loops, poor use of iterations is definitely one. Yeah.
And defining structures or functions which already exist as a library.
Yeah.
So like including the library and
Yeah,
writing the same.
and writing the same thing again. So again, sort of inefficient structure usage. Yeah, that's a good one. Any other thoughts?
Usually printers. You print too many stuff.
Yeah. Well, printing itself causes an overhead. But yes. So perhaps as an example there, if we were writing stuff to a file, and we had 500 print statements, 500 individual print statements in a loop, printing separate variables to a file. That's going to be very slow. We collect them all up at the end, and then write it all at the end, or write it all at the end of the loop, then that's going to be much faster. So yeah, inefficient I/O certainly is one. How many is that? It's probably 4, wasn't it? We've got one more?
Like inefficient or improper use of if constructs?
Definitely, yes. So people tend, for example, not to think about the order that the ifs and else's are executed in their if statement. We should try and understand what our algorithm does, and we should try and put the higher priority ifs at the top, the lower priority ones at the bottom, so we don't have to step through that ladder of if statements until we get down to the one that we actually want to execute spot on. And then there's probably another one as well. And that's down to your domain knowledge, which is using an inefficient algorithm. Yeah. And a lot of people come to programming with expertise in another area. Mathematicians particularly are some of the worst culprits here, because they write code like they write algorithms. Okay? And whilst on paper it might be a beautifully simple algorithm, to understand how that's then implemented in code does cause mathematicians often a little bit of a problem. I'll give you one example. There's somebody I was working with a few weeks ago was writing some code in one of my least favourite languages, which is IDL. A few people giggle there. It's everybody else's least favourite language as well. And she was stepping across a 2D matrix, a 2D array, and she thought it made absolutely no difference at all whether she went across the columns and then down the rows, or down the rows and across the columns. And she thought, well, it's just an algorithm, it should be the same. And then when we used the profiling tool to prove that actually it makes a massive difference, she was not happy. I think the comment was that this is stupid. I hate computers. But there we go. So we've got lots of reasons why our code might not quite behave as we expect. So, profiling the code though, and to be honest, no matter how fast our computer is, some programs simply take too long to run. And eventually, you're going to get very tired of taking coffee breaks every time you need to run a program, and you need to do something about it. Or you want to tackle a problem or a data set that is so large that your program as it stands is never going to complete in any reasonable piece of time, any reasonable interval of time. So trying to make it run quickly, especially for a large program, can be very daunting. But we don't have to make the whole program run quickly. We only have to make the slow bits run quickly. And that's the key difference. And in fact, if we can find the slowest part of our program and make that a tiny bit faster, often that's all the improvement we need to make. So that's what we're going to try and do. So what I've got, hopefully in that SC Leads profiling directory that you downloaded, let me just make sure I can see that myself, is you've got a little program there that calculates parts. Let's have a quick look. Oh, no, I do apologise. I don't think we do try and get any there. So, so we might have to go to the GitHub directory to pop that into a program. So git So if you hit the hyperlink, you're going to see a little MD file, Python profiler. This is what we're going to step through, so a little learning objectives. We've just talked through these. This is the program that we want. Now I'd like to say this is primes.py, so I'm just going to copy all of this stuff. Oops. And just it's all nicely indented.
Can you go back and show where you copied that from?
Yes, if you go back to the Etherpad and wherever it is, not anymore. Somebody's cut it out of the Etherpad. Right, I'll copy and paste that link back in. Just bear with me a second. So I'm going to put this in on line 170. So you'll find a little MD file there. And I'd just like you to copy the contents of primes.py. So I'll just give you a moment to do that. There it is, line 170. Please copy, do not copy if you need to get that, or just click the hyperlink. So if you click the hyperlink, it takes you here. The bit that you want is pythonprofiler.md. There it is. If you scroll down, you'll find a little bit of code. That's the bit that you want. Okay? So all this does is to find the first n prime numbers. So here we are calling it up to 100. So if you take a look at that, you'll see it is essentially just one large function with a call to that function in the main part of the program. So what I want to do is I want to profile that function. I want to examine its behaviour. And to do that, I'm going to add a line just before it. And the line I'm going to add right at the very start is at profile. And that's what we call a decorator. So, have we come across decorators before? No. So, a decorator is like a wrapper we can put around the function to give it some additional capabilities. And what we've added, what we've wrapped around this primes function is the ability to be profiled. Okay? So we've given it the ability to be profiled. So that's all you need to add. What I'd like you to do is just to take a very quick look at this program. I'm not going to ask for any contributions from anybody here, but I would just like you to have a think and maybe make a note. Look at the types of construct we've got here. If we've got loops, if we've got if statements, whatever else we've got, and see if you can work out, see if you can imagine where this program is going to spend most of its time. So it's just a thought, it's just a little thought exercise, and we're going to see whether you're right. Okay, so where do you think this program is going to spend most of its time? I don't need an answer unless anybody wants to say. It's just an opportunity for you to sort of test yourself at the end. So, I'll take that for a minute. So just a minute to test, for you to check rather. Google it. What was // do?
Nicht so viel, wie viel die eine meldet.
So, have we got some thoughts? Most people have made a note why that might be the case. So to run it, and I'm going to show you a printed example as well. So to run it, and hopefully this will work if line profiling is installed properly. Kern prof is the line profile. So you're going to kern prof -l -v primes.py. And then just hit enter. So kern prof -l -v primes.py. Now I think mine is just broke, but fortunately I do have a little example. And you should get a tabular output, which you should get a tabular output that tells you what has happened and how long and how many iterations each part of your program has got. So we've got some interesting data there. Adding the ability to be profiling and then profiling, it has slowed our program's execution down. And there's no real way to avoid that. However, what we've got in our table is some very useful information that then helps us to identify the most expensive, computationally expensive parts of our program. So what you should get is something that looks like this. So it's stepped through the program a line at a time. It's told us how long and how many iterations there have been on each part of that program. Line profile works, just works. But what you might find is that it doesn't speak. So if you use a NumPy function, it will just return how long that function took. It won't tell you how NumPy implemented it. So this is at your Python code level profile. So it doesn't do a deep dive or anything, but it won't work quite well on Cycling code or NumPy code. You just get how long that particular function, that call, that instruction. Which is good. Yeah. Right. And all that does is it just allows you to put in time points. Whereas this profiles the whole program.
Did you maybe?
So, you've got to say, run the profile on the code. Have you got a problem?
Yeah.
Or are you going to have a go at fixing it? So we've not got very much longer, but which was the slowest bit of the code? Or rather, which is the slowest bit of the code that's easiest to fix? Do we think?
Probably, yeah, so this is...
So there's a line up here. Line, which line is it? Yeah, line 9, where I've calculated the route using the built-in power function. Well, that's mathematically a perfectly sensible way, is it not, of working out the square root of a number and raising the power of math, no problem at all. But there are better ways of doing it. So what I would like you to do, and this is just to finish off and see whether it makes an impact. Let's go back to our terminal. Let's go back into prime. So there's another way of doing it. We can use it. We can use one of the built-in math functions. So what I can do. So I can say, do they? Right, what half the people do?
Yeah.
That's annoying. So as a quick aside, I can do import math, and then here...
I didn't save the line saying that, perfect.
Yes.
Yeah.
I can do math, it's SQRT. N.
Yes.
So I've identified a possible place where my program is spending a lot of its time. I've tried a simple fix. So now the idea is, have a go at profiling again, see if that's made any difference. So did we, or did we?
Yeah, this round was taken back.
Oh, that's why. Yeah, I'll save it. So all I've done there is put a very simple fix in, and I want you to profile it again and to see whether that has made a difference. So I'm using the square root function from the math library. And let's see if that makes a difference.
Have to change the operation. Have to change this operation to see.
Yes, so I'm thinking, because that seems to take an awful lot of time, doesn't it?
Yeah.
Yeah. So maybe I could do something better. That's all. So that's a perfectly mathematical value working out square roots. But Python tends to be able to do something better than math. Did that
Things would be having the longer structure, the majority.
Okay, so if you try and run a profile code without the full code, you'll get an error. So what you do
all these things they can make even a difference if something it shouldn't be
but the app profile is recognised by the comment simple to it. If you try it, try to check.
the number.
Tiny bit. So, but at least we know that so it's a command that tends to take, it's iterated many times. That's probably one of the most possible.
What can I put it somewhere
You
inside?
can put it somewhere inside. So if we would split that function into a number of smaller functions, and we only want to profile that function, then you can put it as easy to see in the function of the bit we want to profile.
Always profile
That's the best thing to do. Because very quickly, even a short so good procedure, good program, lots of that's the way to do it. You could say 3:30 to 4. Yeah. So we should have a break. It's up to you. So, two new tools today. Debugging using PDB, which seems quite a nice tool. And we've also got this thing now called Line Profiler that we can use to explore efficiencies or inefficiencies in our code. Now, a few of you have tried that to replace with en route, and it didn't make a massive difference. It made a small difference, but at least we know that that's an opportunity for us to work out how to make code more efficient. Now, on that particular note, tomorrow we're going to look at a number of techniques and some libraries and some additional ways of writing program code that will make your code run faster. So, this has allowed us to explore where our inefficiencies are occurring within the code. So the next step, other than just Googling something and saying, is there a faster way of doing square roots, is to be able to learn some techniques to actually write more computationally efficient code. And we're going to do that on two different levels. Okay, so that's tomorrow. So, at the end of that same document you were having a look at, the one that you've copied and pasted at primers.py, there's a little post-class assessments. Okay, something that we can have a little look at tomorrow. So it's optional homework. So there's some optional homework at the bottom. And that's really to have a look at writing two programs that use different methods to calculate pi. Now, I'm not expecting anybody, just Google it. There's loads of different methods to calculate pi. So see if you can write two programs that each use a different method for calculating pi.